varieties, rational varieties we discussed in the last two lectures are the A discriminants, and they have a parametrization. And here's the parametrization for the Horn uniformization of the discriminant of the polynomial in one variable of degree 3. And then we argued that this parametrization tropicalizes gracefully. And then the output of the black box is the Newton polytope. After me, we had Henri Cohen's talk, and he also talked about a very easy, started out by drawing an octahedron. I haven't met octahedral chocolate, but I'm sure there are also octahedral chocolates available. And he gave this example of starting with a particular binary quartic, making two new binary quartics using the Hessian and Jacobian construction. So we have three polynomials in two variables, homogeneous in his case, T1 and T2. And the question is, what is the implicit equation? And miraculously, you get a nice Fermat-like equation. So in general, let me set up in general, what is the problem of implicitization? So the general problem is we're given n polynomials, f1 up to fn, in d unknowns, t1 up to td, and maybe they're honest polynomials. You can generalize this to Laurent or rational functions, but let's just say they're honest polynomials. And we think of this as defining a ring map from a polynomial ring in n variables, x1 up to xn, to a polynomial ring in d variables, t1 up to td, that sends xi to fi. So at the level of spaces, we take spec, we get a geometric map, the opposite. So in this case, the ring map would go from a polynomial ring in three variables, x1, x2, x3, to the polynomial ring in t1 and t2. And the problem is to calculate the kernel of this map. And the kernel, in this case, I forgot, was x1 to the 6th plus x2 to the 4th plus x3 cubed, something like that. Now, what about this kernel? Well, the kernel is a prime ideal, So the problem, the general problem of implicitization is to calculate a generating set or a Grobner basis for this prime ideal. Now, the examples that we've seen, also shown with Mike, seem to suggest that that's sort of an easy problem that Macaulay 2 can handle easily. But as soon as you try this out on some, example that you actually care about, it will not work. So implicitization is, in fact, a very difficult problem. And it's one of those problems where you wait a month or two, and then you kill the process, and you say, Grobner bases are no good, and Macaulay 2 is no good. So that's more often the experience. Now, there are always special cases. There are always beautiful, nice cases like this, coming from number theory or combinatorics or geometry, where you do succeed, but more likely than not, you will fail. So the last lecture today, I'd like to talk about the failure case. So what can you do if you fail? So before you curse Grobner bases, try the following. Try tropical implicitization. So by tropical implicitization, the data are the same. So I have this map given by n polynomials, f1 up to fn, and d unknowns. And rather than calculating so there is this prime ideal I, but I can't get it, right? So it might be principal, or even if it's not principal, I may not be able to get a single polynomial in the ideal I, well, except for the zero polynomial, right? So I may not be able to write down or compute in finite time a single polynomial, non-zero polynomial in I, but there is this prime ideal out there. Now this prime ideal has a tropical variety, tau of I, and the goal of tropical implicitization is to compute the tropical variety directly from f1 up to fn, directly from the map. Well, there's hope. We've seen that we know at least one interesting case, named the case of A discriminants, where this succeeds. So that was the topic of the last lecture, that if the map we're talking about is the Horn uniformization, then we can carry this out. And so in this lecture this morning, I like to address the question what's the level of generality? Can we do this for every polynomial map, or what are the polynomial maps we can do this for? Now, before I sort of talk about the black box in this case, let me ask the following question. So let's suppose we succeed with tropical implicitization. Well, can we actually recover the ideal from its tropicalization? Right? Can we hope to actually get the variety or get these equations from tau of I? And, well, we can't, right? So even in the case of a principal ideal, then we can recover the Newton polytope. That was the stabbing business that I talked about. But, you cannot recover a polynomial from its Newton polytope, right? You have a whole family of polynomials, and you cannot, in general, recover the coefficients. Maybe in some situations you can recover the coefficients of the extreme monomials, but you cannot recover the coefficients. So if you know the Newton polytope, that's the best thing we could hope for. So suppose we have a codimension 2 or codimension 3 situation. What can we recover? And the short answer is there's the Chow polytope, which I will not define explicitly, that will play the role of the Newton polytope, and recovering the Chow polytope is equivalent to the following data. So this is theorem 2.2 in the paper with the Dickenstein and Feichtner, Alicia Dickenstein, Eva Feichtner. So let's say we are in this situation, and C is n minus d. So let me assume we have a variety of codimension C. So what we can do is, again, Mike or Björn give me a term order, or generic weight vector W. Then I can tell for every monomial prime ideal generated by C of the unknowns. So a monomial prime is just an ideal generated by C out of the n variables. I just pick a subset of the variables. And I like to test whether or not such a prime ideal is associated to the initial ideal in W of I. And if so, what is the multiplicity? Now, I'm taking the codimension C. So these are the minimal primes of the initial ideal. So those I can recover, and I can recover their multiplicity, and basically by the same process. So such a monomial prime is associated to the initial monomial ideal if and only if the tropical variety tau of I, which has codimension C, meets the cone. Well, now I take my W here, and rather than just taking the ray emanating in one of the coordinate directions, I take the cone, the orthant, emanating in C coordinate directions, and I count the number of intersection points. So the number of intersection points counted appropriately equals the multiplicity of this minimal prime in W of I. So that's the best we can do. So we can recover the minimal primes together with their multiplicities for all initial monomial ideals. We cannot recover the embedded primes, and we cannot recover the actual primary ideal. Okay? Equivalent way of saying this is if you're familiar with algebraic cycles, so we can recover the algebraic cycle given by all monomial degenerations. If Mike gives me a term order, then the Grobner basis computation means I'm deforming my variety to a scheme, to a monomial scheme, and I cannot recover the monomial scheme, but I can recover the algebraic cycle. And that's the best we can do. And then putting them all together, there's a thing called a Chow polytope, but in any case, that's the best we can do. Okay, so let's take this to be our problem. So our problem is to carry out tropical implicitization. So we're given n polynomials in d variables, and we like to calculate the tropicalization of the image. Okay, let's try a simple test case. Let's try curves. So curves is the special case. So my curves are affine, just to keep it simpler. We could do it projective, but let me say we do affine. So we have one variable, d is equal to 1, and f1 up to fn, let's say, are rational functions in one unknown. Okay, so let's make this a right thing, rational functions in one variable t. Now, so I have n rational functions in one variable. And let me write alpha 1 up to alpha m, all the poles and zeros of all of these functions on the Riemann series. So including infinity. So I write alpha 1, alpha 2. So I have all these rational functions. Each of them has poles and zeros. And I put them all together, including, the point at infinity. So I take all poles and zeros. Now then, of course, I can write fi. I can factor this form, j from 1 up to m, t minus alpha I, and then there's an integer exponent, uij. Okay? So uij, if uij is positive, then that says that the jth point is a root of the ith equation. And if uij is negative, then the jth point is a pole of the ith equation. Now let's observe. If one of the alphas, okay, let me say the next sentence and then it will be obvious. Okay? So, well, really, we have the exponents, they form an m by n matrix of integers. So the row vectors, ui1, ui2, up to uin, they sum to 0 in Rn. And that's what it means. So if you did this factorization without thinking about the point at infinity, then the vectors don't yet sum to 0, but you have to stick in the negative. That's the residue theorem. Okay? So if you add up all the poles and zeros, then you get 0. Right? If you have a rational function, you count. So that would be, if you have one polynomial, these things sum to 0. So either you already sort of stick in the point infinity, you homogenize, and then they will sum to 0, or you simply add in one extra row vector u that accounts for what happens at infinity. You have to account at infinity, which of these rational functions have poles and zeros at infinity. And that's what you do. That's the answer. Okay? The union of these rays is the tropical curve. So tau of I, the tropicalization of the image, is a one-dimensional polyhedral fan. It's a finite union of one-dimensional cones in Rn. And the cones we take are the cones generated, by these row vectors, the u's. So that's it. That's pretty easy. So implicitizing curves is very easy. And tropically implicitizing curves is very easy. And the reason it's easy is because we have the fundamental theorem of algebra. The fundamental theorem of algebra says, over an algebraic closed field, polynomials in one variable can be factored like this. Let's do a numerical example. So make sure that this is, before we go on, I like to make sure that this example is completely clear. So let's say, and this I think will also clarify Björn's question one more time. Let's look at a plane curve. So this is a plane curve that has this parametrization. Okay, so t2 squared, t minus 1 to the 1, t minus 3 cubed. So I like to calculate the implicit equation. Okay, so I type this in, I wait 2 months, okay, I'm unhappy, and now I try it tropically. Okay, so the tropical curve is this picture. Right? So I have a total of 4 distinct factors appearing, and I simply take these column vectors of the exponent. So I draw the vectors 2, 5, 1, 2, 0, 1, and 3, 1. So those are the 4 blue vectors that point into the first orphan. But then, for the valuation at infinity, I have to stick in this -6, -9 vector. Right? So the way we're counting is this x has a pole of order 6 at infinity, and this y has a pole of order 9. So now I have 5 vectors that sum to 0, and the union of these 5 rays in the plane, that is the tropical curve. Now, is it possible, right, to recover the equation from this data? Well, not quite, but we can recover the Newton polytope. Right? So is there a polytope that has this normal fan? Well, you have a bunch of segments that sum to 0, so that's a no-brainer, right? So there you go. There's the Newton polytope. Okay, so this, you just concatenate these segments, you rotate by 90 degrees, and there in blue is the Newton polytope of the answer. So this Newton polygon in the plane, that's the output of tropical implicitization. Tropical implicitization says, I give this parametrically presented curve in the plane, and then I get, by this observation on the left, I get this polygon. Now, a posteriori, I can say, this polygon, has a certain number of lattice points, so what are the coefficients? And now, I can go to my friends who do numerical linear algebra, or who do, linear algebra mod 13 really fast, and I can recover the coefficients, and there they are. It's some little polynomial. Okay, so there we go. Okay, there's the polynomial. It has 17 terms, so it's not so big. You can do it easily. But see even this tiny example. So there's a coefficient 5 million, 51 million actually. Okay. So that is the implicit equation. So this we like to do in general. We like to do this for any map from D space to N space, given by n polynomials in D variables. Is there a question about this example? I'm going to tell you the general theorem.
If you had a much bigger example, and if you didn't care about all the coefficients, but you just cared about the coefficients along the boundary, would that
Very good question.
be easier to do?
Josephine will answer this question in 20 minutes, 25 minutes. So yes, you can get something. You can get partial information. Okay, so how do we do this in general? Well, we ask our algebraic geometry friends. Oh, I should have mentioned this. So talking about algebraic geometry friends. So, okay, this is actually joint work with Genya Tebelev and Josephine Yu. And Genya Tebelev is an algebraic geometer, work in progress. So there's no paper yet, and he's an algebraic geometer at the University of Texas in Austin. So you ask your algebraic geometry friends, and they will say the following. Well, that's easy, they will say, right? What you do is you look at the divisor defined by these things. So f1 up to fn, they're polynomials, rational functions. So you compactify, right? You take your affine space and you pick a smooth compactification. And then, if these f1 up to fn define a normal crossing divisor with smooth components on a good compactification, then a similar thing works. Okay? That's what they tell you. This is part of an ongoing project with Paul Hacking, Sean Keel, and Tebelev. So they have a general theorem that will appear in one of their papers that says roughly this. So that if, and in fact, many theorems in algebraic geometry are like this. So if you want to study, some situation, often you have this. So if you have, a bunch of divisors on a smooth projective variety, and everything is normal crossing, right? Then you can do this. Now in this case we're okay, right? We have points on the line. The line is smooth, a bunch of points. Now that's certainly a normal crossing divisor, so it worked fine, right? Now, the trouble with these kind of statements is how can you make this computational, right? I mean, are you ever in this situation? So that's why I put the if very big. So there's a very, very big, big, big if. This big black if says, if we are in this situation, then a similar construction works. Now in applications of algebraic geometry, the if never holds. Okay? We never have a smooth normal crossing divisor on a smooth projective right. Never. Okay? In computational biology, in algebraic statistics, in all the applications I've ever run into, you never have normal crossing smooth divisors. Ever. Okay? Now that's not too bad, right? Because we have resolution of singularities, at least in characteristic 0. And so we can resolve easy, right? We can get into this situation by resolution of singularities. True. But that's usually harder than the original problem. Keep in mind, what's the problem we tried to solve? We tried to implicitize a map, right? Sure, we could, apply resolution, so resolution of singularities is now implemented in a really bad implementation in Maple and sort of bad implementation in Singular. So in principle, we could apply resolution of singularities in characteristic 0 computationally and get ourselves in this situation. But first of all, that really doesn't terminate. And if it terminates, you really, really, really don't want to see the output. Okay? Okay, so that's true. And so what we need is we need situations that sort of get us into this normal crossing situation. And we had such a situation in the Horn uniformization. So in the Horn uniformization, I said the word matroid. I said we have to look at the matroid really, really hard. And that's exactly what the matroid does. It desingularizes the hyperplane arrangement for you. So the underlying geometry, the divisors, is that of hyperplane arrangements. There is an existing theory, combinatorial theory of hyperplane arrangements, and the word matroid does the magic in the discriminant setting. So today I like to focus on Newton polytopes of the Fi, toric methods, that will do a similar magic under a certain hypothesis. So we need a hypothesis on our polynomials. And that's the genericity hypothesis. So the genericity assumption I will make now is that my polynomials have random coefficients relative to the given Newton polytopes. So here's my problem again. So I'm given n polynomials in d variables, and I'm going to assume that the coefficients of Fi are generic relative to fixing the Newton polytope Pi of Fi. Okay? So I'm fixing n, polytopes in D space, or maybe monomial sets of monomials, let's say. So I'm prescribing what monomials my Fi are allowed to use, and after I'm done with that, I'm picking my coefficients at random. That's the hypothesis. Now, so my data, really, the data of what I'm about to tell are really not n polynomials in D space, they're really n polytopes in D space. Now I'm going to represent these polytopes by a system of linear inequalities. So I'm going to choose an M by D matrix A and column vectors B1 up to Bn in Rm such that the ith Newton polytope Pi is a solution set to the linear inequalities Au greater equal Bi. So what is these AI? What is this A? Geometrically, well, I have a whole bunch of polytopes. Like I have a Toblerone, I have Henri's octahedron, I have a cube, I have a whole bunch of polytopes floating around. I look at the facet normals of all of these polytopes. And those are the rows of my matrix A. Okay? So if I have a cube and a Toblerone skewed to each other, then M would be 11. Okay? So I take all the normals to all the facets, codimension 1 faces, and then I get this presentation, and then the BI's, so BI is the vector of displacements, how far, so if the ith polytope is the Toblerone, then the BI tells me, you know, how big the Toblerone is. How big do I take? So, for instance, plane curves, parametrically represented plane curves, the data would look like this. So I have n equals 2, I have two polynomials, n equals 2, in d equals 1 variable, right? So I'm given two one-dimensional polytopes, P1 and P2. Now they're given to me. All I know is the left end alpha and the right end beta. These are integers. So this data really is 4 integers. Alpha less than beta and gamma less than delta. Now if I have a one-dimensional polytope, it only has two facets, left and right. So m is 2, right? So therefore the matrix A has entries 1 and -1, and then B1 and B2 are these column vectors. Okay. Now I need a combinatorial structure. So now I need a combinatorial structure that plays the role of the tau of kernel of A. Remember we had this tau of kernel of A yesterday. And the role that's played here is the so-called incidence fan. So the incidence fan is a fan in a big space. So I'm going now to an n plus m dimensional space, R n plus m. So remember, n is the dimension my polytopes are in, and m is the total number of facet directions. So I'm going into R n plus m. I'm going to define the incidence fan of my polytopes. Well, in this space, I'm going to pick a basis. So this is the coordinate basis. I'm going to denote it by lowercase e1 up to en. So these are basis vectors that correspond to my polytopes, my given polytopes. And then I have a second group of basis vectors, capital E1 up to capital EM. They correspond to the facet directions of these polytopes. Now, what do I mean by a coordinate fan? A coordinate fan, I simply mean, you know, a union of cones spanned by these basis vectors. So a simplicial complex, if you wish. Right? So I'm going to tell you a union, a bunch of coordinate planes. And actually, I'm going to take the positive cones. So I'm going to tell you a bunch of subsets of these basis vectors. And for each of these subsets, I'm going to take the cone spanned by them. And that thing I'm going to call the incidence fan. And the rule is fairly simple. Okay, so I have to tell you when to include so a general cone looks like this. So this is the cone generated by EI1 up to EIK, lowercase, and EJ1 up to EJL, uppercase. And I have to tell you whether or not to include that cone in the incidence fan. Here's the condition. So I look at, so E1 up to EK, I1 up to IK, those index K of my given polytopes. So I look at those polytopes, PI1 up to PIK, and I look at their Minkowski sum. Now J1 up to JL, they are facet directions of each of these P's. So therefore, they are facet directions of this Minkowski sum. So I intersect the corresponding facets, and I get a face. So look at the face of this partial Minkowski sum, Pi1 plus Pik, that's indexed by J1 up to JL. And I want this thing to have big dimension. I want this face to be big. And the condition is it has to have codimension at most L. Okay? The L equals 0 case is a little special. So if L is 0, so if we only have lowercase e's, then what we do is we take the boundary of the n-1 simplex. Then we take the proper subsets of E1 up to EK. So if L is positive, it's this rule. And if L is 0, we take all subsets except the following. So this is a union of cones, of coordinate orthons in the n plus m dimensional space, and it only depends on the polytopes pi and how they are positioned relative to each other. Okay, here's the theorem. Maybe I'm going to take this slide away so you remember there is a fan, purely combinatorial fan in n plus m space. And I'm going to use it. The theorem says that the tropical variety I seek, the tropical implicitization, is the image of this incidence fan under a linear map. Remember I talked about a linear map yesterday, right? I talked about projecting onto this space over there. Same thing. Yeah? So we take the tropical variety that I'm after is the image of the incidence fan under a certain linear map from, well, Rn plus m into Rn, right? I'm trying to build a fan in Rn, and I'm given a fan, an easy combinatorial fan in Rn plus m. So I just have to give you a linear map, and then it's the image. It's going to be the image. And here's the linear map. So I take a vector y comma z, so I have y1 up to yn, and z1 up to zm, and I write them as row vectors. Then I form the matrix B, and that's the matrix whose columns are the bi. So that's an n, let's get this right. I'm sorry. That's, I always get this wrong. Do I want, no, that's okay. The columns are the bi. So that's an m by n matrix, okay? So I have an m by n matrix, and I multiply a row vector on the left. That makes a row vector of length n. That's okay. So this is it's the m by n matrix whose columns are those bi. So over there you see the example in the one-dimensional case. And that's it. I just take y plus zb, and that's the fit. So the case we will be particularly interested in, where this will be most useful, is the hypersurface case. So if the image is a hypersurface, then the ideal I seek is a principal ideal generated by some big unknown polynomial g with many terms. And we get as a corollary, together with the stabbing lemma, we get a combinatorial rule for constructing the Newton polytope of G directly from P1 up to Pn. Let me show you how this works in dimension 1. Maybe let's do this. Let's do a multimedia sort of thing here. Okay, so there's our data, right? So now we're going to apply that to the one-dimensional case. So we're given two one-dimensional Newton polytopes, and they look like this. And the output will be the Newton polytope polygon of the implicit equation. But now we have a genericity hypothesis. So the genericity hypothesis says that the coefficients are generic relative to these Newton polytopes. So the only poles, they are sort of, the first polynomial has roots, right, and poles, maybe. The second one has roots, but they don't coincide. The only roots they can share is 0 and infinity, right? So there are only 4 relevant roots. There's sort of the bunch of roots of f, they are together. The bunch of roots of g but then, 0 and infinity, that's special. Okay? So, therefore, all of these polygons in this case will be quadrangles. And there's a case distinction, depending whether or not alpha, so it depends, you have to distinguish whether or not the origin is in the red segment or not. So, and there are 4 cases, and that's the answer. So that's the complete answer, and that's applying this theorem to these data. So let me wrap up my part of the presentation by showing the picture in dimension 1. So in dimension 1, if I have n equals 2 polytopes in d equals 1 dimensions, then there's the incidence span. So I'm n plus m is 4, so I'm in 4-dimensional space, and I'm the incidence span. Then I map in by the map z plus yb, and then I draw the segments, and there we go. And there are 4 cases, depending or not, depending on the position of the origin relative to P1 and P2. There will be 4 shapes, and the analytic formula of these polygons is on the left-hand side. So this works, and you should always think about alpha as being, 1,000, beta being, very big. So alpha, beta, gamma, delta are big integers. Okay, so that's the end of what I had to say. So we're going to get an early start on student presentations. So Josephine, you will take over now and do the analogous picture, present the analogous picture for 3. We start not with 2 one-dimensional polytopes, but we start with 3 two-dimensional polytopes. I'm going to set this up, and I think we can take questions in the meantime, because it will take a minute, I think, for the system to warm up.
So if you do have the exclusion from polygons of your heads, but you only have 3 rings, so in one direction, so slice in one direction, go back in one direction, can you get the answer?
You get partial information.
You don't need the whole information to get the information with respect to one direction. Or you need the whole information?
No. So if you have partial information, you get partial output.
So Bernd, what might be something like a bicubic spline? So a map of P1 plus P1 and P3, given as a bunch of 3, 3.
Gee, Doug, I wonder how that would work, right? So that's right. So let me answer this question by putting on one more slide. So I talked about the case where we have polynomials in one variable. Now, the special case of this, there's a special case where we have products, f of t times f tilde of another t. Right? So we're going to have a surface in 3 space, and that's a very beautiful case. And that was something I wanted to include, but we didn't have time. So I'd like to talk about this. Okay.
Actually, the question I had about it also was, does it handle base case if they all, anyway, we'll talk about it.
Well, that's all. I mean, if it has base points,
yeah.
That's what this is about.
Yeah.
Right? This is the picture of the base points. That's what this is all about. Okay, Joseph.
Okay. Let me start by reviewing the problem. So the problem, the implicitization problem we want to solve is we input 3 polynomials in 2 variables, and we want to output the Newton polytope of the implicit equations. So 3 polynomials in 2 variables have a unique, irreducible algebraic relation, and we want to find the Newton polytope of that. So the 3 polynomials are green polynomial, blue polynomial, and red polynomial. So the rest of the talk will be color-coded pictures. So, and then you can see that each of the polynomials have 3 terms in it. So these are the Newton polygons of this green polynomial, blue polynomial, and the red polynomial. So in this case, we pick them so that the normal directions are all different. So the Minkowski sum, which is the big polygon on the right, has 9 facets, and each of the facets naturally correspond to one of the facets of either green, blue, or red polygons. So we color them accordingly, and then say each blue facet is adjacent to one red and one green, and so on. Okay. So here's the incidence band. So the incidence band is a 12-dimensional, it's a 2-dimensional fan in 12 dimensions. It has 12 rays. So 3 of the rays that are shown by the big dots, the big blue dot, big green dot, and big red dot, they correspond to, so there is one big dot for each of the polygons. And then there is 3 little blue dots. They correspond to the 3 sides of the blue polygon. And 3 little green dots correspond to 3 sides of the green polygons, and 3 small red dots correspond to 3 sides of the red polygons. Okay. So this is a 2-dimensional fan in 12 dimensions. So we intersect the fan with a unit sphere, and you see a graph. So I do the graph there. So in the 12 dimension, the edges don't cross. But in 2 dimension, it's not planar, so I can't draw this. Right, so the edges don't really cross. Okay. And then if you remember Bernd's definition of incidence band, right, so if you look at the big blue dot, it is connected to the other big dots, and then it's connected to the 3 small blue dots. Right? So it has 5 other rays incident to it. And that is true for the big green dot and the big blue, red dot. So they each have 5 rays around it. And then if you look at one of the any one of these small blue dots, right? So they naturally correspond to one of the facets of the Minkowski sum. Right? So if you look at one of these small blue dots, they correspond to one of these blue edges, and then they adjacent to us a red edge and a green edge. Right? So we connect them. So each of the blue dots is connected to one small red dot and one small green dot. So that's the incidence. And then we're going to map into the 3 dimensions. So this lives in 12 dimensions, and everything's nice. And then we map to the 3 dimension, and we get the tropical surface. So this map is given by, I think it was y plus z times b or something. Right? So these are 3, the 3 big dots map to the 3 coordinate directions in a 3 dimension. Okay. And then the other rays get mapped according to the columns or the rows in the B. So I guess the rows in the B. No. Yeah. Okay. So in this case, the matrix B is 9 by 3. So the remaining 9 rays get mapped to these 9 rows. So although in this incident fan, all the edges don't cross and they're all nice, when you map it in, some of the edges cross. So the crossing are given by these black dots. Okay, and then if you look up there, so you see this one green dot and one red dot, they disappear when you map, because if you have 2 cones, and then when you map, they become like this, and then, so, when you map in the blue dot, little blue dot up there, goes onto the edge from the big green dot to the small green dot. And then the small green dot maps to the edge between So the green dot becomes a valent 2 vertex in this graph, and then we don't need to draw them. Okay, so right, so the tropical so in this case we're looking at hypersurface. So the tropical hypersurface is a 2-dimensional fan in 3 dimensions. Right, so we intersect with a sphere, and then we get a planar graph, and this is a planar graph. And so the graph before is an edge graph of this dual of the Newton polytope. So what we're after is the Newton polytope, and then there is this thing called the dual polytope. So the the vertices of the dual polytope correspond to facets of the Newton polytope, and the facets of the dual correspond to vertices of the Newton polytope. Did I say the same thing? So yeah, so you can see that these are essentially the same graphs. So this dual polytope has 14 vertices, 27 edges, and 15 facets. So, and this is the Schlegel diagram of a Newton polytope. What it means is that you have Newton polytope is a three-dimensional polytope, and then there is a pentagonal face. So remember, the big blue dot has 9 edges coming out of it. So the corresponding facet in the Newton polytope is a pentagon. And then so if we take this Newton polytope and we look really closely, so we go really close to this pentagonal face and we look in, and that's what you see. Okay. And then there is also the specially colored green pentagon on the side, and then there is this special red pentagon at the bottom. So there is a blue, green, and red, so they correspond to 3 coordinate directions. And then, right, and the 3 blue rays in the tropical surface correspond to the 3 phases of the Newton polytope. And then there used to be the 3 green rays, but then one of them go away, so now we're left with 2 regular green facets and 2 regular red facets. I could say a little bit about what these facets means. For example, if you take one of these facets, say one of these regular blue facets, right, and then you look at the facet normal, that gives you a weight direction. So if you look at the implicit polynomial, and you take the initial form with this weight, which is given by the facet normal of one of these polynomials, well, you get an initial form, and then you can factor it. So it factors as a monomial times a power of another polynomial, and a power of an irreducible polynomial. So that irreducible polynomial is solution to a different implicit equation where we replace the original 3 polytopes with the initial forms. So there is a facet of this Newton polytope is naturally associated to a direction in this 2-dimensional case. And then,
so this, make one comment. So this addresses both Björn's question and Alicia's question. So this gives us some information about the leading outside coefficients, and it also says exactly in which sense partial information about the input will give partial information about that.
May I ask a question?
yeah, sure.
But once you have the normal, you are not able to recover the polytope because you don't know. I mean, if you have like this, it's a rectangle, but you know, how do you know the size of this rectangle?
Yeah. So this is the same as what Ben said. If you want to get a vertex, right? Then if you're given a generic weight direction, and if you want to pick out a vertex in that direction, so you go there, and then you have a tropical line at that point. Right? So you shoot rays in the coordinate directions, and then you count the number of intersections with multiplicities, like Ben talked about yesterday. So, yeah, it's the same. Right. Yeah. So and then these the green polygon, the red polygon, and the blue polygon that you can see, which is the whole thing, like in the back, right? So, yeah, so they correspond to setting the, so you have this implicit equation P, and they correspond to setting one of these variables to 0. Yeah. So and then the initial form in one of these white directions. right? So they factor as a monomial times a power of an irreducible polynomial and a power of a different irreducible polynomial. And then they, yeah, so they come from the initial form of the adjacent ones. So this is the real Newton polytope that you could see in 3 dimensions, so that there's a pentagon in the back that you couldn't see before. And then, yeah, so you could do linear algebra to try to recover this polynomial, and then in this case there are 154 terms, and 15 of them are extreme monomials corresponding to 15 vertices of the Newton polytope. So they are given in bold in this formula. I couldn't write them all.
That's it.